So we have one final section to look at for this unit, and this section is going to be a little bit different than the rest of the chapter. Section 1.6 is about different types of number systems. And really, this section is just going to be an introduction to all the different types of numbers that will show up in this course. When we looked at section 1.5 about solving linear equations and absolute value equations, you saw that sometimes the answers were really nice number answers, like 4, 6, 7, things like that. Sometimes they were negative numbers, sometimes they were fractions, or could have been written as decimals. You've seen in Algebra 1, sometimes the answers involve taking square roots, and these are all different types of numbers that we need to deal with. What this section is going to involve is defining different types of numbers, classifying them, and trying to figure out how certain types of numbers are related to other types of numbers. And then this will also give us some language that we can use as we move forward through the year. We're going to start with the most basic of numbers, the natural numbers, also sometimes called the counting numbers. Numbers like 1, 2, 3, and so on. And these were really the first types of numbers that were used in civilization by people being able to kind of go out and count the sheep that they had, just count 1, 2, 3, 4, 5, some number that you can count to, the natural numbers. We have a symbol for the natural numbers, and we have symbols for many of these different number systems. Our symbol for the natural numbers is a kind of fancy looking N. I'm going to make a capital N, but I'm going to give it a double stem on the left. That fancy looking N means natural numbers. And what we can do with that symbol is write out a couple statements. For example, 5 is a natural number. I can write that using math notation as 5, this kind of curved looking E, and then our symbol for the natural numbers. I can read this line as 5 is a natural number. 5 is a natural number. Technically, the symbol means is an element of the set of, so 5 is an element of the set of natural numbers. Don't worry about that. Worry about this as 5 is a natural number. 17, that's a natural number. 17 is in our set of natural numbers. 256 is a natural number. 256 is in our natural numbers. Now, as we go through this section, we're also going to build up a diagram that shows how all these different number systems are related. Can you please flip ahead to page 30 in your notes? Relationship between the 8 different number systems. By the time we're done, we'll have 8 different number systems. I'm going to start with the one and only system that I've dealt with so far, the natural numbers. I'm going to draw an oval, and I'm going to write in there natural numbers. And I have numbers like 1, 2, 3, and so on. Make sure you get that in your notes. And we're going to go back to page 25 in the notes. There's actually a lot that we can do with just the natural numbers. I can take any 2 natural numbers, I can add them together and get another natural number. 5 plus 7 gives us 12, another natural number. I can also do any multiplication problem. 9 times 2, natural number times a natural number, gives me 18, another natural number. There's a really important number missing, though. We need, so right now our natural numbers, how many sheep we have? We've got 4 sheep, we've got 256 sheep. But we need a number to represent we have no sheep out there in the fields. The Mayans were the first culture that added 0 into our numbers. And what we're going to do is we're going to make our number system a little bigger, and we're going to call this the whole numbers. Numbers like 0, 1, 2, 3, and so on. The whole numbers are just the natural numbers with 0 thrown in there. we need some number to represent we have, well, nothing left. Sorry, give me one moment, trying to find a page. Okay. The whole numbers really just add 0 into the natural numbers. We don't have a special symbol for the whole numbers, but I can write things like 4 is a, so to show whole numbers, since there's no special symbol, I can write it like this. Whole numbers inside set braces. 4 is in my set of whole numbers. 0 is also in my set of whole numbers. Four is a whole number, 0 is a whole number. Adding this into our diagram, back on page 30, again, the whole numbers include everything that I already have and just add 0 to that. To show this, I'm going to draw a circle around what I already have. And I'm going to call this the whole numbers. Everything on this page is already a whole number, but the whole numbers are also going to add 0 into that. 0, 1, 2, 3, and so on. Those are the whole numbers. Make sure that's copied down. Back on page 25, there are two different types of things we're going to focus on with these number systems. I can give you a number and ask you, is it an example of a natural number or a whole number? That's kind of what I was doing over here. Is 4 a whole number? Sure it is. Is 0 a whole number? Sure it is. But the other question I can ask you is for the best possible classification for certain numbers. And what I'm looking for here is the smallest set of numbers that a particular number would belong to. All three of these numbers are whole numbers, but we might have a smaller set that they belong to. For example, 18 is a whole number, but the best classification, the best name we can give it is natural number, because natural number is the smallest classification that it belongs to. I'm going to label 18 as a natural number. 0, well, is 0 a natural number? No, it's not. Whole number is the best classification for 0. Whole number is the smallest set that 0 belongs to. What about 5? What's the best name for 5? 5, its best name is natural number. 5's best classification is a natural number. Again, all of these are whole numbers, but 18 and 5 can better be classified as a natural number. Now, again, we can do any addition problem, any multiplication problem, but we've got an issue with subtraction. I can take two natural numbers or two whole numbers and subtract them and get another natural number or whole number. For example, if I do the problem 9 minus 4, I get 5. Natural number minus natural number gives us natural number. Or whole number minus whole number gives us another whole number. But could you come up with a subtraction problem involving whole numbers whose answer is not a whole number? Well, actually, what if I just switch the 4 and the 9? If I do 4 minus 9, I get, some number that I don't already have on here. This is also sort of the story of our number systems. Once we run into a mathematical problem involving just the numbers we have, we're going to make our number system a little bit bigger to allow for problems like this. We need a number system that includes negative numbers, and these are going to be the integers. Our integers are numbers like -3, -2, -1, 0, 1, 2, 3, and so on. The natural numbers are really just the whole numbers and their negatives. I think I want to actually add that in there. The integers are the whole numbers and their negatives. The integers are just the whole numbers and their negatives. We do have a special symbol for the integers, and this is a not very obvious letter. We're not going to use I for the integers. The integers were first discussed by German mathematicians, and in German, the word number is Zahlen, which starts with a Z. Therefore, we're going to use a fancy-looking Z for the integers. Now, I can tell you things like -6 is an integer. I can say things like 3 is an integer. It's not its best name, but it counts as an integer. I can tell you that 0 is an integer. To add this into the diagram, back on page 30. Well, I think everything on this page is already an integer, and then I have some other numbers. So how do you think I'm going to show it? I think we just need to circle around everything here, make our number system a little bit bigger. I'm going to label these as the integers. And maybe I won't list them, I'll just put a couple random ones there. -4, -17, 6, 2, 0, whatever. You don't have to use my numbers, you can use your own numbers. Add that into the diagram, please. And, okay, so now we need to do some best possible classifications for some integers. And remember, that question is all about what is the best name we can give to that number. These are certainly all integers, but I want to see if there's a better name, a smaller set that I can name it. Natural numbers, whole numbers, or maybe integers really is the best. What do you think for -17? What's the best name for -17? Well, since it's a negative of a whole number, I think integer is the best we can do there. What about B? What about 0? 0, its best name is whole. I can call that a whole number. What about 17? That's a natural number. I can count up to 17. We'll call that a natural number. So by now, I can take any two integers, I can add them, get another integer, subtract them, get an integer, multiply them, get an integer, but I'm going to run into a little bit of an issue with division. I can do a division problem like 18 divided by 6 and get 3. Integer divided by an integer gives me another integer. Could you come up with a division problem that doesn't give an integer solution? Well, actually, what if I just do 6 divided by 18? That's going to give me a fraction, and I don't yet have a number system that lets me deal with fractions, so I need to make my number system a little bigger so I can deal with fractions. And here enters the rational numbers. Rational has the word ratio in it, and ratio means fraction. Rational numbers are numbers that can be written as fractions. Rational numbers are numbers that can be written as fractions. Rational numbers are numbers that can be written as fractions, but actually it's a little bit more than that. Fractions in the form a over b, where a and b are integers. Fractions where the numerator and denominator are integers. Get that copied down, please. So we have a symbol for rational numbers. And we're not going to use R. We're going to save that for something else in a moment that you might already know. Instead, rational numbers are fractions. Fractions are division problems. Do you know the name of the answer to a division problem? Like the answer to an addition problem is the sum. The answer to a subtraction problem is the difference. What's the answer to a division problem? Well, answer to a division problem is the quotient. And because of that, we're going to use a fancy-looking Q for our rational numbers. Q, I might as well add in Y, from quotient. Because rational numbers really are division problems. Q from quotient. So to give you a few examples, I think 1/7, that's a rational number. Of course, you can write that as a fraction. We already see that it's a fraction. -5/3 is a rational number. We can write that one as a fraction. -5/3. What about 2? Is 2 a rational number? And if so, why? I guess the real question is, could we write 2 as a fraction? Well, sure we could. We could say 2 is just 2/1. That's a fraction where the numerator and denominator are integers. Yeah, 2 counts as a rational number. And for that matter, any integer counts as a rational number. Any integer can be written as a fraction if we just put it over 1. Now, before we move on, let's talk about decimals for a moment. There are 2 types of decimals that are examples of rational numbers. Decimals that either terminate or repeat are rational numbers. Decimals that terminate things like maybe 0.5. Oops, let me move up a little bit. Decimals that terminate or repeat, maybe like 0.3 with a repeating bar over it, are rational numbers. Decimals that terminate, like 0.5, or repeat, like 0.3 repeating, are rational numbers. They're numbers that could have been written as fractions. I know that 0.5 is just a half. I know that 0.3 repeating is just a third. Any terminating or repeating decimal will have a fraction it came from. It's not always easy to find those fractions. We're actually not going to focus on that so much, but we're just going to know that we could find a fraction that would give that decimal. With this in mind, let's go back to page 30. Our diagram. I think I'm just going to keep doing what I've been doing. I think every single thing on this page is already a rational number because I could just put it over 1. So I'm just going to draw a circle around that. My rational numbers include things like a third, -7/5, 0.2, 0.4 repeating, 0.56565656 ... It's not the best way to write it, but it still counts as a repeating decimal. 3. Get that added into your diagram, please. Back to page 26. Not every number, though, can be written as a fraction. There are some numbers that can't, like the square root of 2, like pi. No matter how hard we try, we can't find a fraction that gives us that number. Well, numbers that can't be written as a fraction are called irrational numbers. I'm just going to define this as numbers that cannot be written as fractions. Irrational numbers are numbers that cannot be written as fractions. There's no special symbol for this. And as for the decimals, well, these numbers have decimals that are non-terminating and non-repeating. Decimals that are non-terminating and non-repeating. which actually gives us a nice little test that we can use to figure out if a number is irrational, if it can't be written as a fraction. I think I mentioned to you that the square root of 2 is an irrational number. No special symbol, so I'm just going to say square root of 2 is in my set of irrational numbers. If you go to the calculator and type in the square root of 2, 1.414213562, yeah, that's a decimal that looks like it's going on forever, but I don't see a pattern with that. Pi, probably the most famous example of an irrational number. Pi is an irrational number. Pi is in our set of irrational numbers. Get all that copied down, please. And then we're going to head over to page 30. And we've got our ever-growing diagram over here. How can we fit the irrational numbers into this? Where are those going to go? Not a single thing on this page counts as an irrational number. I need a separate set on the side. I'm going to draw a little circle over there, and I'm going to say irrational numbers. Things like square root of 2, pi, 0.4175602145689 ... Looks like it's going on forever. By the way, to show it's going on forever, you've got to include the ... Goes on forever, but I don't see a pattern there. It's not repeating. Get that added into your diagram, please. Before we start doing some best classification problems, we need to move on to our sixth number system. We've seen a whole lot of numbers so far. And actually, these are all the numbers that you've seen in Algebra 1. Fractions, square roots, all that good stuff. I need some way to group. Oh, you know what? Sorry, I'm jumping further ahead than I should. Ignore what I just said. Let's take a look at the numbers on the top of page 27. Got a whole bunch of numbers here, and I want to classify them just as rational or irrational. Could they be written as a fraction, or could they not be? And we can always use that decimal rule to kind of test things, look at the number as a decimal, and see if the decimal seems to be terminating or repeating, or non-terminating, non-repeating. I know some of these have better names, but all I'm going for is it rational or is it irrational? What do you think about letter A? Rational or irrational? Well, could letter A be written as a fraction? Sure it could. It's already a fraction. It's just 1/4. That means it is a rational number. How about letter B? 2. Is 2 rational or irrational? I could definitely write this as a fraction. I could just put it over 1. That makes it a rational number. Square root of 3. What do you think? Well, if you're not sure, let's take a look on the calculator. Square root of 3. 1.7320508. It goes on forever. I don't see a pattern there. That is an irrational number. Square root of 3 is an irrational number. How about letter D, square root of 4? Not every square root is an irrational number. Square root of 4 is just 2, which, like letter B, makes it a rational number. Letter E, pi. Again, probably the most famous example of an irrational number. Pi is an irrational number. 2/7. 2/7 is a rational number. Of course, we can write it as a fraction, just 2/7. G, 0.167 repeating. Repeating decimals, remember, are rational. If I tried really hard, I could come up with a fraction that would give me that particular decimal. I just don't know off the top of my head. Letter H. Letter H, well, that decimal that goes on forever with no pattern, that's an irrational number. Irrational number. Next, and this is what I started talking about earlier before I was really ready to talk about it. These are all the types of numbers that you saw in Algebra 1. We just want some way of grouping them all together, some umbrella name for all these different types of numbers. We're going to call this umbrella the real numbers. A real number is any rational or irrational number. The real numbers include any rational number and any irrational number. All the irrational numbers are real. All the rational numbers are real. There's a special symbol for the real numbers. This is what I was saving the R for. A couple of examples. I don't know, 1/4 is a real number. 0 is a real number. Square root of 11 is a real number. Anything that is rational or irrational. Really, any of those numbers you saw in Algebra 1. To add this into a diagram, page 30. I told you that the real numbers are really just an umbrella name for all those types of numbers that we've dealt with so far. So I'm just going to draw a box around the whole thing. And I'm going to call this box the real numbers. There is no possible number where real is the best name. Any real number can be better classified as either rational or irrational. And actually, if it's rational, you might be able to do even better than rational. I'm not going to bother adding in any more examples because every single thing on this page is a real number. Let's do some best possible classification problems. Bottom of page 27. That is not easy to see. Let me zoom in a little bit. Okay, all these numbers, these are all real numbers, but I want to come up with the best possible classification for them. Letter A, what's the best classification for -4? Well, it's a negative of a whole number. That's going to make it an integer. Its best name is integer. What about B, 2/7? It's a number written as a fraction, and I can't really do any better than that, so we're going to call this a rational number. Square root of 8. Square root of 8, well, maybe use the calculator to check this one. Square root of 8, yeah, it's a decimal that goes on forever with no pattern. That's going to be an irrational number. 0. 0 is the only number where whole is its best name. Square root of 9. Don't be fooled by the square root. Square root of 9 is just 3, which is a natural number. 2 plus the square root of 7. Well, I think the best way to think about this is square root of 7, that's an irrational number. Its decimal would go on forever with no pattern. If you add 2 to that, it's still a decimal that goes on forever with no pattern. Yeah, a decimal that goes on forever with no pattern. This thing is an irrational number. Again, please notice, I did not use the word real anywhere here. Real will never be the best possible name. And we can now do a whole lot of math just using all these real numbers. We can add any two real numbers, subtract them, multiply them, divide them. I can do square roots. But actually, there's one thing we still can't do. There are a bunch of square roots I can do. I can do the square root of 9, I can get 3. I can do square root of 8 and get a decimal or a simplified root. I can do square root of 5/7. It's not going to be pretty, but I can do it. But there are some numbers you can't take square roots of. you remember what those numbers are? You learned in Algebra 1 you can't do square roots of negative numbers. You would say no solution or something like that in Algebra 1. Well, we're not in Algebra 1 anymore, we're in Algebra 2. And we're going to do what mathematicians do when they run into issues like this. You can't do square root of negative 4? Well, let's just invent a bigger number system that would let us deal with problems like the square root of 4. They needed something that was sort of the opposite of a real number, so they came up with imaginary numbers. Imaginary numbers are square roots of negative numbers. Imaginary numbers are square roots of negative numbers. No fancy symbol. The square root of negative 1 is an imaginary number. You would not have been able to handle something like that in Algebra 1. Square root of Algebra 1 is in our set of imaginary numbers. Square root of negative 5 is in our set of imaginary numbers. Negative the square root of 9 is in our set of imaginary numbers. Oh, wait a minute. Is it? Is negative the square root of 9 an imaginary number? Actually, no, it's not. This is just negative 3. It's not in our set of imaginary numbers. It's an integer. It's a real number. The negative has got to be underneath the square root for it to be an imaginary number. Now, adding this into our diagram. Any ideas? Just circle around everything or something different? What do you think? I don't think anything on this page is an imaginary number, so I'm going to put a little set on the side. I'm going to label this box the imaginary numbers. And I'm going to include things like square root of negative 4, square root of negative 7, square root of negative 5. Those are all imaginary numbers. Get that added in. I've got one more number system. And this is going to be sort of like our real numbers. I want some number system that really just sort of is an umbrella group for absolutely every possible number we could end up with in Algebra 2. And these are called the complex numbers. This number system is just going to group everything together. A complex number is either a real number or an imaginary number or, I'm not going to tell you the third one yet. We'll figure that out in a moment. Get that copy down, please. We do have a symbol for the complex numbers, and it is the obvious symbol. We're just going to use a C with a double stem over there. I think that 5 is a complex number. Way better names than complex, but it counts as a complex number. I think that the square root of negative 8 is a complex number. Imaginary is a better term, but it counts as a complex number. There's one more type of number, though. 5 plus the square root of negative 8. Well, the 5 is a real number. The square root of negative 8 is an imaginary number. This, well, it's not real because of the square root of negative 8, but it's also not imaginary because of the plus 5. It counts as a complex number, and this is my third type of complex number. If I have the sum, or difference for that matter, of a real and imaginary number. The sum of a real and imaginary number. In this unit, we're really just talking about vocabulary for these things, but in the next unit, we'll see how to actually work with numbers that are imaginary and complex. And in the following unit, we'll start seeing equations that have answers that might be imaginary or complex. Adding this into the diagram on page 30. Every single thing on this page is complex. I'm going to draw a box around everything. Label this as the complex numbers. And I'll also add in something like 2 plus the square root of negative 3. You know what, why don't I also add in 5, square root of negative 7, 0, a couple other random numbers. Any number that's already on the page is complex. This is the only type of number whose best name is complex. Add that in, please. Okay, so on the bottom of page 28, I would like to find the best possible classifications for several numbers. It's going to focus. Wonderful. I would like you to, these are all complex numbers. I want to come up with the best possible name for those numbers. See what you can do. What do you think about A, 16/11? What's the best name? Well, it's a fraction. It can't be simplified to anything else, so I'm going to call this a rational number. What about B? It's a fraction, but I can simplify that down to 2. We've seen 2 several times already. 2 is a natural number. Letter C. Negative 16/4. That's just negative 4. That's an integer. Make sure you are simplifying these before you name them. Letter D. Well, because it's the square root of a negative number, that's all it takes for it to be an imaginary number. Letter E, square root of 2. We've seen this one a few times already. That's an irrational number. 3 plus square root of negative 4. That's a complex number. And this is the only type of number whose best name is complex because it's a real number plus an imaginary number. How about G? Hope you weren't fooled by this one. 3 minus the square root of 4. Well, square root of 4 is 2. This is 3 minus 2. That's 1. That's a natural number. Letter H, what about 0? Whole number. What about letter I, 0.13, repeating? Repeating decimals, remember, are rational numbers. So that's rational. 0.134, repeating. Another repeating decimal, that's rational. 2 more decimals. Letter K. That one, that's an irrational number. It's a decimal that goes on forever with no pattern. By the way, if it didn't have the ... at the end, it would be a rational number because technically it would be terminating. The ... is really important there. Finally, letter L. Another decimal that goes on forever, but this one does look like it's repeating, 0.16 repeating. Certainly not the best way to write it, but that's okay. It still counts as a rational number. Last thing we're going to look at. I want to spend a little bit of time talking about these true-false questions, which you're going to see in the homework, and this is also sort of our chance to practice with those symbols. The way these true-false questions work is I'm not asking you if a particular number system is the best classification for a number, just is it any sort of classification for a particular number. In letter A, it's asking, is 14 in my set of, remind me, what does Z stand for again? Z, that's the integers. Is 14 an integer? Well, integer is not the best name for it. Natural number is the best name. But does 14 count as an integer? Absolutely it does. I'm going to make this true. That's what we're going to do for these. Not, is it the best name? Just, is it any sort of classification for that number? B, square root of 11. Is square root of 11 in my, well, whatever Q stands for? Hopefully remember that Q is rational. Is square root of 11 a rational number? No, it's a decimal that goes on forever with no pattern. False. Letter C, what do you think? Is the square root of 16 a rational number? Well, square root of 16 is 4. Can you write 4 as a fraction? Absolutely, you can. True. Letter D, negative the square root of 25 is irrational. True or false? This is saying, is negative 5 an irrational number? I don't think so. I think it's rational. I think you could write it as a fraction. False. Letter E. You know what? I don't even have to look at my number in letter E. Is it a complex number? I don't care. Absolutely anything is a complex number. True. If I want to be more specific, this is a real number. In fact, it's an irrational number, which makes it a real number, but all real numbers are types of complex numbers. It is true. Letter F. This is just 13. Is 13 natural? Absolutely it is. Letter G. Yeah, that's not a real number because of that square root of a negative there. It's false. Letter H. Is 17.5 a real number? Sure, it's a rational number, and rational numbers are real. That's going to be true. Letter I, almost there. Letter I, what do you think? Whole numbers do not include negative numbers. That one's going to be false. Letter J. Because of the 8, it's not imaginary. If it was just the square root of negative 9, it would be imaginary, but because of the 8, it is not. That has to be false. Finally, letter K. Is that imaginary? Sure it is. It's just the square root of a negative number. That is true. Again, the point of this section was to just expose you to all the different types of numbers we will encounter in this class. We will see 3 units from now, when we start dealing with certain equations, maybe the answer is going to be the square root of negative 17, or 8 minus the square root of negative 9, or something like that. We will learn ways of simplifying these in Unit 2, and then start getting numbers like these as answers in Unit 3. See you later.